and low pressure, real gases turn into liquid. I think that's where we ended the conversation, yes. Then the next conversation we ended up having carried on from that point where at low temperature, low pressure, real gases tend to liquefy, like the liquids in an aerosol can for either air freshener, deodorant, or even a gas cylinder that cooks. Then we spoke about the ideal gas laws, which apply under strict conditions. And then we went on to derive how we come up with there's a formula for pressure, volume, the number of moles, a gas constant, and temperature. PV equals nRT. Do you remember that formula?
I'm just trying to scramble through the notes to see if I remember it.
Okay.
PV equals
nRT. Remember when I made a comment about the meme on a car license plate?
Yes.
That formula. Yes. So we went on to discuss that, and then we talked about Boyle's law. So Boyle's law is simply tells us that the pressure of a fixed quantity of gas is inversely proportional to the volume it occupies if the temperature remains constant. So let me just share screen so you can see um, which one am I gonna share? Okay. Yeah, I'm gonna open that Jamboard. So let me charge this so long. Okay, tablet's charged. Then I can charge pen. Yeah, I needed an excuse to charge the pen. So I'm gonna open this one and then share screen. Yeah, that way this way. Yes, so this was the conversation where we carry on from real gases versus ideal gases, where they liquefy at low temperature, low pressure. Then we started the conversation on deriving this formula from the ideal gas laws, which apply, which are these laws, they form the general gas equation and they form the ideal gas equation. So this next set of slides is going to be a discussion of that. But first things first, the measurements for pressure, they are in atmospheres, 1 atmosphere equaling 760 millimeters of mercury, or 101.3 kilopascals, or 101,325 pascal. So the 760 millimeters of mercury comes from, if you take a pan filled with mercury and you invert a test tube into it, the pressure of the air of the atmosphere, which equals 1 atmosphere of air pressure, will shoot the mercury up that tube to a measurement of 760 millimeters. So that is also a standard measurement. It's a very basic way of measuring air pressure using elements, really. But that's it. And then when you use force divided by area, you'll get that as the number corresponding to both the two. So that was just a note I made. The volume is typically measured in liters or cubic decimeters, but we'll refer to cubic decimeters or dm cubed. And 1 liter, or rather 1 cubic meter, is 1,000 liters or 1,000 dm cubed, or 1,000,000 cubic centimeters. So car engines, what's the size engine of your what's the size of engine for your car?
I don't know. A 1.5.
1.5. So that's 1,500 cubic centimeters. So that means you would have 1,000 of those, like 1,000, yeah, maybe roughly just under 1,000 of those to make 1 cubic meter. So if you think about 1 meter by 1 meter by 1 meter volume, you could fit 1,000 1-liter milk cartons in there. That's 1 cubic meter. That's 1,000 liters. So if you are to think about now cubic centimeters, which is a smaller unit of measure, if you take on your ruler a measurement of a centimeter and you cube it, so you multiply it across its area and then you give it a height so that it forms like a small box, like the size of a die, then 1,000,000 of those would fill up a cubic meter. But 1,000 1-liter milk boxes would fill up a cubic meter. So that's the comparison of volume units. Now, N is the number of moles, like in many of our calculations in chemistry. R is a gas constant, which also has something to do with Avogadro's number, but we'll get to that. And then the temperature is always measured in Kelvin, but to convert from degrees Celsius to Kelvin, you have to add whatever degree Celsius number you have to 273 to get the Kelvin. So the first law that we discuss is Boyle's law. I think Boyle was a British scientist, and he identified that the pressure of a fixed quantity of gas is inversely proportional to the volume, provided that the temperature doesn't change. So in other words, if you think of an aerosol can, there's too much pressure in here, in the can. That's why we don't heat them up, otherwise they explode because of the pressure. The heat makes the particles move too much in the thing, and they can even cause the metal to pop, and that's why you get an explosion. So at the point of the nozzle, when you press the spray nozzle, at that point there where the gas emits, that's where you get a pressure change. So from the can into the tube there, the pressure is high. But there, at that juncture, the pressure is low. So things tend to move from a region of low pressure to high pressure to low pressure. And that's why the gas can diffuse out like that, because there's too little pressure there. And because gas particles are high energy, they need more space to move. That's why it just disperses like that. But the graphical illustration, if you want to visualize it as a mathematical graph, as the volume increases, then the pressure decreases. And again with the nozzle, big volume, small pressure. Small volume, high pressure. Then that ties now into the kinetic theory of gases, where small volume means the particles have a small space to move in. They therefore have too much kinetic energy, and that means that there's high pressure, because the pressure tells us about the kinetic energy of the particles in that space. Too many of them, they have too much high energy, and the pressurized container makes them move a lot. But if the volume is big, the particles have more room to move. They have little kinetic energy. So far, so good?
Yes, let's go to the lungs.
All right, so the lungs also express the same thing. When you're breathing in, I normally would practice that during meditation, but when you're breathing in, there is, as you're breathing in, you increase the volume of your lungs. Your lungs take up a lot of air. This pushes your diaphragm down to increase the space in your rib cage. But as that volume increases, the pressure decreases. The pressure in the rib cage decreases. Now when you breathe out, your diaphragm pushes up against your lungs, and when it pushes up against your lungs, it increases the pressure in your lungs, and decreases the volume, and then you can breathe out. So that's another way to think about the pressure volume dynamic in one's body. We did an example, but these ones are explained in the videos that, again, we're shifting to fiber, so once that's set up, it'll be quicker to upload my things, because yeah, they take a while to get uploaded. They're too large. Let me just put it like that. 2 hours of a video is quite heavy. It's like 2 gigs at a go. So that's why I've been struggling to upload them, and I'm not on Fiverr yet. But anyway, this will be explained better in the videos that you can watch. And then there's a second law called Charles' law, another chemist, but he explored the relationship between volume and temperature. And his relationship was that as the volume increases, so does the temperature, provided the pressure remains constant. And the formula there is this. But what that just means is at 0 degrees, you have a certain volume and it increases. But as the temperature goes into the negatives and it gets to 0 Kelvin, not 0 degrees Celsius, 0 Kelvin, which is negative 273 degrees Celsius, or absolute zero, then you have the smallest possible volume for your gas. We then did some calcs with the same thing, but it's just punching in numbers if you're given the details of the gases. Again, it's straightforward calculations. Then the next law that we explored was that between pressure and temperature. And again, it's that one way at low temperatures, gases become liquid. And that's the formula that we use in those calculations. Again, they're also substitution. There's just a few considerations to note, like which units to use. Then we went on to have the general gas equation, which combines the relationship Boyle, the relationship of pressure versus temperature, and the relationship of temperature and volume. And it gives us this formula here. Now, as we move forward in these slides, I want you to think about your experiences with a pressure cooker. You've used one before, right?
I have one.
You have, okay. So it's going to get really interesting because this one you'll be easily able to relate to. But in any case, with the, what's this one? The general gas equation. Remember in the first slide, we started with general gas equation and ideal gas equation. So the general gas equation is PV divided by temperature equals a constant. But in the first instance where the temperature, volume, and pressure are a certain measure, after some time and there's been some change in that system, we can equate the two and we can work out the differences between either. And an example we used was a truck moving. The speed is not really defined, but we're looking at the tire pressure. And it's found that the tire pressure is a certain pressure at a certain volume at a certain temperature. So let's assume the truck is driving on the N1. It traveled in the morning when it was cooler, and then it got to its destination, maybe somewhere in Northern Cape where it's very hot, and the volume is increased because the wheels have warmed up and the temperature's gone up, and then we can find the pressure there. And we do indeed find that between those two times, the pressure did indeed increase. So that's one application. And then there's the ideal gas equation, which takes into account Avogadro's law. And Avogadro's law simply tells us that the same volume of different gases means the same number of particles. Before I get into that, I wanted to talk about pressure cooker. So you normally have the same volume. You don't change the volume of the pressure cooker, yes?
Yeah, that's correct.
But what happens if you change the pressure?
You have to release it. You can't necessarily change it.
Yeah, you do change it when you release it. So it's high pressure before you release it, and when you release it,
it's low inside the vessel.
Inside the vessel. And then something happens to the food, right?
Yeah,
It cooks. Yes. So that's the fascinating thing, because the mere fact that changing the pressure also changes the physical properties of the food means that somewhere inside the temperature has to change. And that's what's explained by this relationship. So that's where the pressure cooker gets its cooking principle. So I just wanted to share that because I find it fascinating. But yeah, okay. So ideal gas equation takes account Avogadro's law, and when we introduce the number of moles of the substance, where the number of moles means the number of particles in a certain volume. So it doesn't matter what gas you have. In one empty bottle, even if you put chlorine gas or carbon dioxide gas or oxygen gas or nitrogen gas, you will have the same number of particles for either substance in one set size of volume. And then we use that to work out a couple of problems. And that was it. So from there, we stopped at solutions where we looked at how we can use this you remember that conversation on stoichiometric coefficients? That example of burning propane, where that means propane is mixed with oxygen and it gives carbon dioxide and water. Remember that calculation? Yeah. So we can, given the volume of one, let's say we have the volume of the propane, we can find out how much volume of oxygen we need so that we can burn that much volume of propane. And we use a stoichiometric coefficient. Then again, we can also work out these. Then the next part of our conversation, which extended from that, was to work out the molar concentration of substances. And we did an example where we had a volume of a solution of sodium chloride, and from that volume we could work out the concentration, and then from that concentration we found the number of moles, and from that number of moles we could work back to the mass of sodium chloride that was needed to produce that concentration of solution for that volume. So I just wanted to recap on that class so that you don't miss out on where the conversation has been going to here where we are now. So then we continued our conversation from that sodium chloride example where we worked out the concentration, because it takes us to the three types of reactions, right? So these three types of reactions are precipitation reactions. You ever seen when you're mixing something and then after the reaction has happened, some residue is left at the bottom of a tank or a flask or whatever?
Yeah.
So those are precipitation reactions. Yeah?
I'm saying titration.
Titration, yes. So then the next type of reaction is acid-base, where we typically have an acid, like a sour tasting substance, literally, like stomach acid or vinegar, and a base, a soapy substance, tends to be bitter, like bile and soap. But these usually, when mixed, result in a salt and water. And then there's reduction oxidation reactions, where electrons get transferred and some electrical energy can get measured from that. So these are in our grade 10 textbook from page 314 onwards. So on Classroom, you'll find that, and then we can carry on like that. Then in grade 11, the conversation adds to that to say from acid-base reactions, we can do titration, where we accurately witness the point where chemical equilibrium is reached, right? And you typically have a pipette that drips one solution of a certain concentration and a certain volume, which you read off the graduations of the pipette. As the dripping gets into the volume that's also known of the other substance that's getting titrated. And then when you see the chemical change, because you typically have an indicator in the one substance, the indicator doesn't react with the substance in there, but when there is a change, it changes color to show that you've reached the point of equilibrium. So now those calculations, they're done using this formula here. The concentration of substance A, which maybe you'd find in there, times its volume, which you would read from the graduation there, divide by the stoichiometric coefficient. So when you have a balanced chemical equation, the stoichiometric coefficient of the compound that's in there would equal the concentration in here times the volume of substance in there divided by the stoichiometric coefficient. And an example of that is sodium hydroxide, which is used in cream relaxer, and hydrochloric acid, which tends to be found in stomach acid. But in you know what? Let's just go through this theory. Let's just go through this theory so that if we did it before, then it will be reinforcement. That's fine. We're almost out of time. So the 4 types of problems for empirical and molecular formula in grade 10 are: 1, we have formula and must find percent mass. The second type, we have percentage composition. So we have percentage composition, and we must find a formula. 3, we will be given products and we must find one of reactant. So find one reactant. And then 4, yes, we did talk about this. We find the waters of crystallization. I believe, Nobuhle, you missed that part of waters of crystallization. But it's fine, we're gonna crystallization. So I don't know if you've, but we did this when we did geology, ne? So some molecules, it would be a crystal. Like a geological formation is typically a crystalline form. So it would be like a crystalline version of aluminium and something else, like aluminium chloride or something like that. But and depending on how much water it has, or if it has no water, let's say the water's been dried up, it will be anhydrous. Or if it is hydrous, then you'll see it'll be maybe, let's say it's aluminium something. Let me look for an actual example. An actual example would look something. Yeah, let's say AlCl3, and then it'll be multiplied, so to speak, with like 6 units of water. So these types are these ones here, right? So molecular and empirical formulae, these are important because they give us a sense of how to write out the chemical formulae, right? And but we'll do a class on this should there be a need. But I just want to introduce this concept from here. Right. So if we have, for example, vinegar, well, let me rather put here grade 11. On page, this is page what? Page 303. Page 303. All right, cool. So let's say we have an example. We've got vinegar, which we find in our home, and it's a dilute form of acetic acid. So we're given acetic acid, and it has the following composition. It is 39.9% carbon. It is 6.7% hydrogen, and it is 53.4% oxygen. We are asked to find the empirical formula. So this is pretty much like one of the types that we talked about now, one of the 4 types. So we must find the empirical formula. Now, how do we do that? If we take a nominal mass, so take nominal mass, and that nominal mass is 100 grams, then by that definition, we have 39.9 grams of carbon, 6.7 grams of hydrogen, and 53.4 grams of oxygen. So I use the word nominal, Musa. The word nominal just means a number that's convenient for us to solve. So nominal means convenient for us to be able to solve the problem. So it's a convenient number. Okay. And then we can work out the number of moles for each. And with that, we use these masses. So remember, the number of moles is the mass divided by molar mass. So we'll take 39.9 and we divide it by the molar mass of carbon is 12 on the periodic table. Hydrogen is 1.01 and oxygen is 16. Then we find the answers to that. So here we've got 3.325 mole. Here we've got 6.337 mole. And here we also got 3.3375 mole. So that means the empirical formula, if we divide by the smallest number, which is 3.325, we will have, so let's make a table. So we've got carbon, hydrogen, oxygen. The smallest number, so here we've got 3.325, 6.6337, and 3.3375. So dividing by the smallest number gives us 1. This one gets us close to 2, and this one gets us close to 1. So empirically, the formula would be C, 1C, 2 hydrogens, and 1 oxygen. And if we want to find the molecular formula, which is part 2 of the question, we're given the molar mass of acetic acid as 60.06 grams per mole. So with that information, we can find the actual number of moles. But I'll just leave it here. It's not a tough calculation, but I'll just leave it here because I'm seeing the thing is going to close now, the call, in like 2 minutes. Yeah, 3 minutes. But yeah, let's just use our 3 minutes to quickly, I just want to find out, is everything so far clear? What we discussed. Are there any questions? Before the call cuts.
Titration.
What about titration?
If you can just run through it a little bit in the next session that we'll have.
More titration. Okay, got it. Mosa? When are you are sharp? Okay. No worries. Thank you so much. I'll see you on Thursday. Tomorrow we are not having class. Alright. See you all Thursday. Sharp.